Hey there, it's me, Miss B, and this video we're just looking at the end of Unit 4 review assignment for my class. So this isn't actually an assignment from Illustrative Math Algebra 1. This is a review assignment, but these questions come from the material. So looking at question 1, we're asked what would be an appropriate domain and range for each situation. So function A gives the area of a square in square centimeters as a function of its side length s in centimeters. So for domain, that is the basically all possible input values. So domain, and our input here, it does tell us it gives the area as a function of side length. So it's the function of side length s in centimeters. This is the input. And then the area of the square is the output. So a reasonable or appropriate domain for this is, since it's a distance and we're measuring it, no negative numbers. I like to ask myself if negatives or 0 make sense, or if fractions make sense, because those are the three general areas that we would tend to exclude from real life situations depending on context. In this case, centimeters, we can use partial centimeters. Centimeters are not only whole numbers, but an actual box or a square would have to have dimensions and area. So we're going to say that this would be we can say like all positive numbers another way to say it, since this would be an x value, we could, or it gave us the variable s, we could say that s is greater than 0. Now technically we could input 0 as a length, and we would get 0 for an area, but that just means that our square doesn't exist. So I would argue that it's greater than 0 and not greater than or equal to. Now the range of this is the outputs, or the y values, or in this case the area values, and that's dependent on our values for the input. So if we can't input 0, that means we can't output 0. And if we're not inputting negatives, we're not going to get answers related to those. So we just have to think about the s being positive. And we can square pretty much any number, so this should be accurate to say the same sort of thing, all positive numbers. And we could say that a of s is greater than 0, because the statement a of s represents the output value when s is the input. So we're just saying, hey, that has to be bigger than 0. And that would be a reasonable domain and range. So we're going to do that same process for the next two, and I probably won't take as long explaining each. So for part B, we have function Q, and this is the number of people going on a bus, or I'm sorry, it's the number of buses needed for a field trip, and the number of people going on the trip is n. So it's as a function of the number of people. This is my input. And Q is the number of buses. This is the output. So domain, we're going to describe the number of people. Going on the trip. Now we could say 0 because nobody signs up for the field trip. So that would work. We could say, well, we couldn't say, is what's more important. We couldn't say negative. And with number of people, we also can't use fractions. It's whole numbers only. So this is going to be, you can say whole numbers, or the mathematical word is integer. So integers, integers, and I would say greater than or equal to 0. Okay, the range is essentially going to be the same thing. It's going to be whole numbers. You can't have a fraction of a bus. Even if a bus is a different size, bigger or smaller or something like that, it's not going to be a fractional amount. It's whole numbers only. And if 0 people are going, then 0 buses are needed. So I would also argue for this one that integers greater than or equal to 0. If they gave us more detail, like each bus could fit a certain amount of people, then we could actually be more specific and say, like, it's multiples of 5. But in this case, they don't give us any detail for that. So for part C, we have function v giving the total number of visitors to a theme park as a function of days since a new attraction was open to the public. Now, domain here is going to be our input. So domain. And the input that we're using is days since the new attraction was open to the public. We could actually use negative numbers here because it's just a new attraction. It doesn't mean that the theme park itself wasn't open. So negative numbers is fine. But generally, I would argue that this should also be something that's just measured each day. They normally measure total attendance. So I would say that this is integers. So that D, or we can just say whole numbers, or integers. And negatives is fine because we can count backwards beforehand. It would actually be interesting to see the change from the opening day of this ride. Now, for our range, this is in number of visitors. And so visitors is people. And with people, we don't do fractions. So it is going to be whole numbers or integers again. We also don't do negatives, and I would probably argue that the range is not going to be 0, that we wouldn't have 0 people attending this theme park. So we can say, but it is possible to have 0, so maybe no people showed up, but we just absolutely cannot have negative. So we can say, for this one, it is integers greater than or equal to 0, or whole numbers 0 and above. So I'm going to use the same description that I gave for the one above, which is just integers greater than or equal to 0. And you could say the second part of these as an inequality. So I could say integers, and then I could say v greater than or equal to 0 instead of writing that whole thing out. So that does apply for the ones above as well. So let's look at number 2. We're now trying to state domain and range based on this graph. All right. So the first thing I notice is that my graph does not go to negative numbers. I only have number of bagels and best price in dollars. So 0 and 0 is part of our input and our output. If I'm just looking at domain, I have from the left to the right. And so in this case, it goes 0 to 13, and that is going to be my domain. So we can say domain and it does look like this is whole numbers only, which would make sense. I'm pretty sure there's not too many bagel shops or coffee shops or wherever they're buying these bagels that they would let you buy a portion of one. I mean, maybe half, but we're going to say it's whole numbers or integers. So we can say integers. And then I'm going to express this as an inequality. So maybe where, or, no, let's continue with words. So I'm going to say integers from 0 to 13. They didn't actually define a variable for us for bagels, otherwise I would have used that as part of an inequality, but I didn't want to start just defining random variables here, so that's why we're using words. For our range is prices. Now it looks like our maximum here was maybe 1150. That estimate is based on the fact that these on the left-hand side are going every 2, so that 11 is going to be about halfway, and the last x there looks like it's just above 11, but not quite 12. The 11 looks like it should be here, so maybe this is 1150 or 1125. Since we're not entirely sure, I'm going to use 1150 because that is the maximum that's shown on this graph. And with domain and range, we're only going to state the range that is shown to us. So this is not necessarily whole numbers, though. So it does include 0, but it's, it's dollars, so we're allowed to include cents and things like that. So we can say, we'll say all numbers for simplicity. We can say all numbers from 0 to 11.50. If we want to be more specific, we can somehow express that it is only allowed to be in dollars and cents, so only 2 digits past the decimal point, and so maybe like rounded to the nearest hundredth, which is the second place after the decimal, so hundredth. I'm never quite sure if there's an extra D in there for hundredth or not, but we're going to go with that spelling. Okay, and let's look at number 3. Tyler filled up his bathtub, took a bath, and then drained the tub. This function gives the depth of the water in inches 2 minutes after he began to fill the bathtub. So these statements describe how the water level in the tub was changing over time. we want to use the statements to sketch an approximate graph of the function. Okay. What we are told by this first one, b of 0 equals 0, is that there is no water in the tub to start. So that looks to me like, you know what, I'll do this one in red, but 0, 0. I like to do my graphs, I think, in red just so they stand out a little more. So 0, 0. Now we know at 1 minute, the level of water in the tub at 1 minute is less than the level of the water in the tub at 7 minutes. So I am going to have to look at like 1 minute and 5, 7 minutes. I'm just marking some places for input values on my graph that I'm going to have to be careful. Since they're not giving us specific amounts for those two, I don't have to put a specific point. But the third piece of information they give us is a specific point. This is that b of 9 equals 12. So that is that at 9 minutes, there is, or I just said 12, b of 9 equals 11. And that at 9 minutes, there is 11 inches of water in this bathtub. So very specifically, we're going to look at 9 minutes. So 9 minutes would be right about here. And then there is 11 inches. So that's going to be right about here because it needs to be just a little over 10. So that looks like a good spot to put that point. Okay, let's keep looking. Our fourth piece of information here is that the level of the bath at 10 minutes is equal to the level of the bath at 23 minutes. So b of 10 equals b of 23, which means they don't give us a specific value, but we know that it's flat at that point. So I'm also going to make some marks on my horizontal axis here. So that was at 10 and 23. So I'm going to make myself a mark here. And at 23 should be right about there. I know it needs to be flat in that area, or at least needs to be equal. And the last piece of information is that b of 20 is greater than b of 40. So I'm also going to have, and I'm going to mark these near my axis, but a little bit below, so that I know they're related to each other. Okay, so first things first, I think Tyler is probably just filling up this tub. So I have my starting point, and I have a point that I know it needs to go through, which is here. Now, that's not to say it can't go even further up, but I know I do need to hit this point. So let's put this, I don't know, right about here. I'm going to make just a flat line. Now, I do need to make sure that at 1 minute it was greater than at 7 minutes. And because I am increasing at a positive rate here and a constant rate, 1 minute is going to be greater than 7 minutes. So we're good on that one. I'm going to erase those marks because I just took care of them and made sure those were accurate. Okay, so now 10 and 23, those were equal. I could just say, hey, at this point, Tyler's taking his bath, and it's going to be flat from those points to those points. So 10 and 23. And the level of water at 20 minutes is supposed to be greater than the level of water at 40 minutes. So from here, I could just say that maybe he's just emptying his tub, and it looks like this. And that does satisfy all of my conditions because the level of water at 20 minutes is here, and at 40 minutes it's here. So 40 minutes is less water. 10 and 23 is constant. I have my one specific point, and I know it's increasing here from 1 minute and 7 minutes. So all of those pieces are satisfied. So this would work as an approximate graph of the function. Filling up the tub, taking a bath, and then emptying the tub. So continuing on, let's look at number 4 here. W is the weight of a puppy in pounds as a function of its age t in months. So we want to describe the meaning of each statement in function notation and create a graph that could be a representation here. So W of 2 equals 5. Let's describe that statement. So weight and months. Our input value is what's inside the parentheses. So this says, essentially, the weight at 2 months is 5. So I always like to think of an equal sign being the word is. So this says the weight at 2 months is 5. And that's how we're going to basically define all of these. The weight at 2 months is 5 pounds. For our second statement, we can read it the same way. The weight at 6 months is greater than the weight at 4 months. They don't tell us what the weight is, but we know that the puppy weighs more at 6 months than it does at 4 months. Okay, and for the very last statement, we have that the weight at 12 months is the same or is equal to the weight at 15 months. Now we might actually just say the puppy weighed the same at 12 months as it did at 15, but you're always welcome to just write this out in almost exactly the way it's written mathematically, the weight at 12 months. Is the same as the weight at 15 months. Okay, so now we want to create a graph that could represent this function and to label our axes appropriately. So I am going to say that time is our input because that is what is inside our parentheses here. So that is months. And then pounds would be the label I would put on the side here. Okay, the weight at 2 months is 5 pounds. Since everything here, this goes to 10, but I believe that means that these are measured in fives. So in twos. So 2, 4, 6, 8, 10. Yeah, so each one of these is 2, meaning that if we have the weight at 2 months, that's going to be on our first axis line here. Okay. So oops, did I accidentally switch the page? My bad. Let's put a point there. So 2 months, 5 pounds. And the other axis is the same essentially. So this goes in twos, 2, 4, 6, 8, 10. So 5 is actually going to be halfway right here. So we are going to have this. 2 months, 5 pounds for our first point. At 6 is greater than at 4. So puppy's going to be increasing in weight. And then at 12 is equal to 15. So 10. So 12 months would be here. 13, 14, 15 would be here. So we're going to make sure that those are equal. And then we have 1, 2, 3, 4 months and 6 months. We just need to make sure the puppy's increasing in weight. Okay, I am not going to start this necessarily at 0 because the puppy is going to weigh something when it's born, but we're going to start it slightly above 0. And we can just say that our puppy is growing. It's probably going to grow at a different rate than this, but that's okay. And then at some point, puppy's going to stop growing. I know that puppies grow for longer than 9 or 10 months, but you know what? We're okay to just sort of continue it here because maybe the puppy has reached its adult weight. But it does satisfy all of these conditions here. And that is our important point. And maybe it's I don't know, maybe it's the way that it grows. So it's okay to have straight lines here, although curves might be appropriate as well. You just need to make sure that your graph satisfies all the conditions given to you and is reasonable. Okay, let's look at question 5. Ooh. All right, this one is a piecewise function. Function C represents the dollar cost of renting a bike from a bike sharing service for t minutes. Here are the rules describing the function. So we want to complete the table with the costs for the given lengths of time. This is in minutes and dollars. So my price chart is at the top. So 0 minutes. We can't actually rent a bike for 0 minutes because it's not allowed to be equal to 0. It is just greater than. So this is undefined. Now, we can use 10 minutes, and that is in our first price point, which is between 0 and 30. So that is the 250. We can do 25 minutes. That is also going to be in that first range, so that will also be 250. If we rented it for 60 minutes, that would put us at the very end of the second step, which would be $5. 75 puts us in the third step here, which is between the 60 to 90 minutes, and that one is $7.50. 130 puts us in the fifth range here. We're actually going to skip over the 90 to 120, and this is taking us to the $12.50 price level, and 180 would give us the very last one, the $15 price range. Okay, so if we want to sketch a graph for this that are at least 0 minutes and at most 240, well, it already told me 0 minutes is not allowed, but the first price range from 0 to 30 minutes is $2.50. So at 0, we're going to put an open circle around the 2.5 because it could start at 0, but it's not going to ever be equal to it. And then we'll put a closed circle at 30, because if you rented a bike for exactly 30 minutes, you would get charged that original rate of 250. Okay, the next step here goes from 30 to 60, and that is at 5. So we need to put an open circle here, right? Because this is our $5 price point. Open circle. And then we're going to take this over to the 60 minutes, which is the upper end cap here. Put a line in between. Let's find the endpoints of our next one. This one goes from 60 to 90 at 750, so from 60 to 90. Our next one goes from 90 to 120, and that's at $10, so from 90 to 120. here. We have 120 to 150, so that's the 1250 price point, 1250. And then lastly, we have the price from 150 to 720. But for this graph, it's 240 minutes. They said at most 240, so that's all we're going to put our graph for. That is going to go from 150 to 240 over here, although technically our graph will extend, but at most for our graph. So we're going to look like this. Okay, and I think that one was just completing the graph. Yep. So we're going to continue on over to question 6. Question 6 gives us a function for parking. So we have C as the cost, H is the hours in the parking lot at the stadium. It can be represented with this piecewise equation. So we have this over here. This means this is our dollar amount that we're paying to park. These are our limits on hours for each price. What do the numbers 3, 6, 10, and 15 mean? We're going to say they are the possible outputs, which is cost of parking. Okay, so how would you explain the parking rates in words? So let's zoom in a little bit more on this, that way you can see better what I'm talking about. For the first 30 minutes, it's $3. For the next 30 minutes, it's $6. Then we have for 1 to 2 hours, it's 10. And for 2 to 8 hours, it's 15. So they don't necessarily have a consistent thing saying like a certain amount every certain amount of hours. So we're just going to describe those. We'll say $3 for the first 30 minutes, or half an hour, since this is in hours. Half an hour. $30 minutes, $3 for the first 30 minutes, which is half an hour. $6 for 30 to 60 minutes. We can say $10 for up to 2 hours, and $15 for up to 8 hours. And if you wanted to reword the second step there with the 6, you could say $6 for up to an hour. Because technically the 30 minutes is not, you're not being charged for that in the $6 range. Okay, let's look at number 7. The function c gives the cost of renting some equipment for n number of hours, and it's defined by this equation. We have 8.25n plus 30. So what does the original function tell us about the situation? What does the inverse tell us? And then we're going to look at the cost of being $112 and how many hours was it rented for. So the original function tells us a couple things. I have a flat amount that I'm starting with, so 30. That's not going to change no matter how many hours I rent for. But the coefficient on n tells us the price per hour. So we can say that it is $8.25 per hour plus $30 fee. What is the inverse of the function, and what does it tell us about this situation? Well, let's find the inverse. So we're going to do that by solving for n, meaning we're going to take our equation here and do some operations on it. So c equals 8.25 n plus 30. Let's subtract 30 from both sides. I like to do PEMDAS, but in the reverse order when solving, right? So if we have adding 30, we're going to subtract it, deal with our adding and subtracting first. So now we have c minus 30 equals 8.25n. That means now we're just multiplying by that 8.25. So to get n by itself, we're going to divide, which is the opposite of multiply. They're inverse operations. We're going to divide both sides by 8.25. So what happens then is that on this side, it'll cancel out, and we'll be left with n equals c minus 30 divided by 8.25. So this is my inverse, so I'll put a little box around that. And it says, it tells us the number of hours based on the cost. Okay. And so for the very last part, we're going to use our inverse function here. It says if the cost is of $112.50, how many hours was the equipment rented for? So let's do this one. We're going to say the cost was $112.50. So we're going to use n. Oops. N equals, and whenever I plug things in, I like to put them in parentheses. So instead of c, I'm going to put in parentheses 112.50. That is going to be minus 30. And then the entire thing gets divided by 8.25. Okay, so 112, 12, or 1250. If we subtract 30, that's going to give us 82.5. So we're going to have n equals 82.5 divided by 8.25. So same numbers, but just one decimal place different. And if we divide that by 8.25, we're going to get 10. So n is equal to 10. So the equipment was rented for 10 hours. Okay. And I think we still have a couple more questions, so I'm going to keep going over to the next page. Yes, we do. We have question 8 here. So we have at a party, hexagonal tables, basically tables in the shape of hexagons, which means 6 sides, are placed side by side as shown here. If S equals 4n plus 2 represents the number of seats as a function of the number of tables, n, we want to write an equation to represent the inverse of the given function. So explain what the inverse function tells us and how many tables are needed if 94 are attending the party. So tables is n and seats is s. We want to solve for n because this is already solved for s. So we want to get n by itself. That means we need to subtract first from both sides. Then we're going to divide both sides by 4. So that would be s minus 2 divided by 4. And this is going to be equal to just n. That's my inverse right there. Don't need to do anything further. What does it tell us? The number of tables because n was the number of tables, so it's going to tell us the number of tables based on the number of seats. Or you could say the number of tables with a specific amount of, or when there are a specific amount of seats. So if 94 people are attending the party, that's question C, we want to explain how many tables. So we're going to say 94 is our number of seats. We're going to use our inverse function that n is s minus 2 over 4. So we will say n is, I need 94 seats minus 2. Divide that whole thing by 4. Put that in my parentheses, but this is now 92 divided by 4. And if we do 92 divided by 4, we actually get a whole number. We get 23. So how many tables are needed if 94 are attending the party? 23 tables are needed. Now it says justify your answer. My justification is the work that I'm showing here. So hopefully that work speaks for itself, but if you're not showing your work, you need to explain how you got to those answers. We are not going to accept just giving a number. We do have to have some sort of explanation, but showing your work is a good explanation. So 23 tables are needed. And that is actually the last question on this review assignment. So thank you for sticking with me through this assignment, and good luck on your test.